Well, good morning, class. This is an example. We're going to start with kind of a review of where we've been and help us launch to where we're going. But if this sequence is arithmetic, meaning that if I'm growing by a common difference each time, I'm adding or I'm subtracting the same value each time I move forward by one, what is the explicit equation for this sequence and what is the recursive definition for this sequence? So I'll go ahead and put the question marks up here. So I want us to find the missing terms to complete the table. I would like for us to write the explicit equation for this sequence, and I would like for us to write the recursive definition for this sequence. So if you want, go ahead and pause the video and try this on your own. If not, I'm just going to go ahead and continue to work through this now. So I need to figure out what I'm adding each time as I move forward. And in order to figure that out, essentially I'm finding the slope, the rate that I'm growing by. So I'm going to go ahead and take the number 9 and subtract 7 from that. So what you can see is I'm taking this output and I'm subtracting this output. And in my denominator, I'm going to take the 6 and I'm going to subtract 3. So I'm taking this input and I'm subtracting this input from it. When I do this, my numerator ends up being the number 2, right? 9 minus 7 is 2, and my denominator ends up being the number 3. So what I know is that as I move forward, I keep adding 2/3. I add 2/3, I add 2/3. So if I was to take this and look at it as a fraction, I could take 7 plus, and I'm literally using my calculator off screen, so 7, and it would be 7 2/3, but I think I'm going to write these as improper fractions. So expressed as thirds, 7 is the number 21/3, right? That's the number 7. And in fact, 9, let's see, 3 times 9 is 27. This is the number 27/3. So this is kind of a cute trick. 21 plus 2 would be 23/3. 23 plus 2 would be 25/3. And then 25 plus 2 is 27/3, which does indeed reduce to the number 9, right? 27/3 is 9. So looking at these as thirds makes this easier for me to think about. If I move backwards, instead of adding 2/3, I need to subtract 2/3. So if I take the number, what is it, 7, I'll take the number 7 and I will subtract 2/3. So 7 minus 2/3 is going to be 19/3. And again, you can think about that as 21/3 minus 2/3 is 19/3. And then 19/3 minus another 2/3 should be 17/3. And if I go one more, right, if I subtract 2/3 again, I end up getting 15/3. And I'm going to write this number here, 15/3, which is the number 5. And the reason why this is significant is that is my 0th term. And that will be very helpful in writing the explicit equation for this sequence. So I think I have everything I need. Let's go ahead and put the pieces together. So the explicit equation for this sequence, I could say that t of n, the output at any spot, is equal to, I'm growing by 2/3, so I'll say 2/3 times n plus my 0th term. I can either write as the number 5, or it might even be more helpful to write it as 15/3, but obviously either is correct. So this is my explicit rule. So if I want to know at any particular point, I just plug in that value and it'll tell me. So example, if I was to put 6 in for n, right, if I was to put 6 in, it should give me the number 9. Well, 2 times 6 is 12, so I have 12/3 plus 15/3. 12 plus 15 is indeed 27, and 27/3 is indeed the number 9. So I can see, at least with that point, I tested it and it's functioning. Probably I could put 3 in also. If I put 3 in, that would give me 2 times 3 is 6. 6/3 plus 15/3. 6 plus 15 is 21. 21 thirds, yeah. So I'm convinced that, that's functioning properly. Okay, so now let's look at the recursive definition. So the recursive definition always needs two parts. It needs the rule about how to move forward. So this is from yesterday's talk or the talk before, but I could say, hey, the next term in the sequence, the next one, right? So you're at one term, but the next term in the sequence is equal to the term that you're currently at plus 2/3 more, right? So the next term is the term that you're at plus 2/3 more. Turns out that's not enough information alone, because you also need to tell it how to move forward. So what we typically do is give it the starting point. So we can say, hey, and by the way, the very first term where you begin is the number 17 thirds. So now I have the two pieces of information I need for the recursive definition. I'm telling people, where do I start? I start at 17 thirds. And how do I move forwards? I move forwards by adding 2/3. And you can see that's exactly what's happening here. I start at 17 thirds. And 17 thirds plus 2/3 is 19 thirds. 19, 20, 21 is 21 thirds, which is 7. Plus 2 more thirds is 23 thirds. Plus 2 more is 25 thirds. Plus 2 more is 27 thirds. So absolutely, this is the recursive definition for this sequence. And let me just say this again. To get to the next term in the sequence is equal to the term that you're at plus 2/3. And the very first term, the starting point, is 17 thirds. All right, so let's continue then on. Today we are jumping into lesson 5.2.3, and we're focusing again on sequences, but today we're looking more at geometric sequences, which we haven't looked at a lot. So in the past few lessons, we've investigated sequences that grow by adding, arithmetic sequences, and sequences that grow by multiplying, geometric. Yesterday, I think in part B in one of those, there was a relationship there that was not arithmetic, it was not geometric. It was, I believe, a quadratic relationship. So in today's lesson, you're going to learn more about growth by multiplication as you use your understanding of geometric sequences and multipliers to solve problems. As you work, use the following questions to guide your team's discussions. And the questions are, what type of sequence is this and how do we know? There's only really two that we're thinking about. So what kind is this? How do we know it's that kind? How can we describe the growth for this particular sequence? And how can we be sure that our multiplier is the correct value? So question 92. Thanks to millions of teens around the world seeking to be just like their math teachers, no one believes that to be true, industry analysts predict that the sales of the new Pi phone will skyrocket. API, teenagers, and Hollywood celebrities are expected to flock to an exclusive shop in Beverly Hills, California today, clamoring to pick up their new Pi phones. The Pi phone releases began last week when the store pre-sold 100 phones. So it's 0th term. It pre-sold 100 phones. The store expects to sell an average of 15% more this week and each week thereafter. I plan to stand in line all night, said Nellie Hillman. As soon as I own a Pi phone, I'll be the coolest. I'll be cooler than everyone else that I know. All right. So I guess that's the setup for that. Let's talk about this problem. So this article provides a situation for the number of Pi phones the store expects to sell. They start by pre-selling 100 Pi phones. Predict the number sold during the 4th and the 10th week. So the interesting thing is this number 15%, right? I'm growing by 15% each week. What is our multiplier if we're growing by 15%? So I like to think about this. I start with the number 1, and if I've got a percentage growth, I'm adding that percent expressed as a decimal to it. If I'm decreasing by 15%, I would start with the number 1 and I would subtract 0.15. Again, that's 15% expressed as a multiplier. So in this case, right, I have the number 1 plus I'm growing by 15%. So my multiplier, right, what I'm multiplying by each month is 1.15. That's going to keep everything I have and add 15% more every single time I jump forward. So if I started out with 100 PiPhones at the I guess for my pre-sale, I could say I've sold 100, and then I'm going to be multiplying by 1.15. Oops. Raised. I want to put a decimal there. It won't let me. There it is. 1.15 raised to the x power, where x is the number of weeks. That's crazy. I keep writing a decimal and it keeps disappearing. So this expression, 100 times 1.15, should be the expression I could use to figure this out. Now, they're not asking me to get that yet, and I'm grabbing my calculator and kind of looking at this. So I started 100. Oops, let me clear this. So if I wanted to kind of look at this a little bit more cleanly, I might try to set up a table. So let's do that. I'm going to grab the pen and I'm going to draw a table. And I'm going to let n be the number of weeks. And I'm going to let t of n be the number of PiPhones sold. So I can have week 1, 2, 3, 4, 5. Now I know that I start pre-sell 100 phones, and each time I move forward I'm multiplying by 1.15. That's going to keep increasing me by 15%. So I know that in the first week 100 times 1.15 is 115% more, which would be 115 phones. Now if I grab my calculator, I'm going to go 100 and I'm going to ask it to keep multiplying by 1.15. I do see the 100 times 1.15. I do see the 1.15. The next week it is 132 and some change. So I'm not rounding that up to another phone. I'm just going to leave it at 132. But I'm not taking the decimal off either. So about 132. Now if I go to the next month or next week, I'm at 152 and some change. If I go to week 4, I'm at 174.9. So that's interesting. I might report that as 175 phones for week 9 because that's one of the questions, or I might leave it rounded there. So the question's asking me, and again guys, I'm looking at question 92 in the book. You don't see the question, but I do encourage you to look at the book. But it says predict how many phones you would sell for week 4 and for week 10. So my prediction for week 4 is right here, and I just have to keep this going, right? So I'm at 201. I'm at week 6 would be 231. Then I'm at week 7 is 266. Boy, it does not like when I try to write down here. Week 7 I said was 266. Week 8 is 305.9. Week 9 is 351. And week 10 is about 400 and week 10 is about 404, and it's 0.5, so I'll probably just call that about 404 phones. So I've got my two predictions there. Now the store needs to know how many phones to order for the last week of the year. If you knew the number of PiPhones sold during week 51, how can you determine the sales for week 52? Well, that's that's pretty straightforward, right? If I knew how many they sold in week 51, I would just have to multiply that by that value for the next one. So I could say, hey, in order to get week 52, what you do is you're just going to take the number of phones that you sold at week 51 and you're going to multiply it by that 1.15. So I can see here I just keep multiplying by 1.15, which is nice. But it says how many Pi phones should the store predict it will sell during week 52? Well, that's a problem because I don't know how many they sold in week 51, and I'm not really interested in extending this table out this way. So at this point, I want to focus on building out this explicit rule, not the recursive rule. So to do that, I'm going to just say, hey, look, this is very convenient. If I want to know how many phones we're going to sell during any week n, right, I'm taking my 0th term, how many I pre-sold, and I keep multiplying by the multiplier exactly 52 times. Well, I would say I wouldn't put the 52 there. I'd say exactly n times. What's nice about this is now I could just change this number n instead of writing it as a variable, and I could put the number 52 in there, and this expression will give me how many I expect to sell during that week. Now, as a check, I'm going to try it for the 10th week, which is ugly right here. I'm going to plug 10 into this and see if it gives me about 404, just as a check. So I'm going to go 100 times 1.15 raised to the 10th power, and when I do that, I do get the 404.5. So if I run that all the way up to 52, 100 times 1.15 raised to the 52nd power, it's giving me a ridiculous number of phones, right? It's literally giving me 143,313. So way, way out there. If I extended this out, that's where I'm going to land. Okay, let's jump on to question number 93. And we are only going to do 93 and 94. So 93. A new iTalk, a rival to the PiPhone, is about to be introduced. It is cheaper than the PiPhone, so more models are expected to sell. The manufacturer plans to make and sell 10,000 pre-orders and expects sales to increase by 7% each week. Okay, so again, we're talking about a percent increase, so I'm going to have my 1 plus this 7% expressed as a percent, right? 7% expressed as a decimal, rather. So as a decimal, that would be 0.07. So my multiplier here is going to be 1.07. That's 100% of what I have, and then plus, right, and I'm increasing by 7% every single time. So first thing, it says write an explicit, let me put this up here. Write an explicit and a recursive equation for the number of iTalks sold during the nth week. Okay, so let's start with our explicit equation. I think I have enough room for that right up here. So we're doing 10,000 pre-order, pre-sale. So I'm going to say T of n equals 10,000 phones times 1.07, and I'm going to raise that to the nth power. So this is the same model I had before, right? It's my initial pre-sale, my 0th term, and every single time I move forward, I'm multiplying by 1.07. Now, the recursive part needs two things, right? I need to know how do I move forward, and I also need to know where I start. So I'm going to say, look, if I know, if I want to know the next week, right, the T of n plus 1, that's the next one. If I want to know the next one in the sequence, I'm going to take that, the next one will equal the one that I'm at, the T of n week, and then times 1.07. So you can see what's happening here is that I'm taking the value that I'm at, T of n, and I'm multiplying it by the multiplier, right? My multiplier here is 1.07 because I have a 7% increase. Now that's not enough. The other thing that I need to include for the recursive definition is I need to include, I can say the 0th week, T of 0, the one before the one I write down in my sequence, my pre-orders, is 10,000 phones. Those two things together are the recursive definition. Where do I start and how do I move forward? And the top thing that we wrote down is our explicit rule. All right, what if the expected weekly sales increase was 17% instead of 7%? How would the new now what would the new explicit equation be, and how would you change the recursive equation? So the only thing that would be different in both of these equations is instead of using a multiplier of 1.07, if I have a 17% and it's increasing, not a decrease, but 17% increasing, I'm going to take 1.17, and that's going to become my multiplier. At that point, two things change, right? My multiplier is 1.17. That's going to be reflected here in my recursive sequence, and it's going to be reflected here in my explicit sequence. And then finally, well, that's it for that. That's it for question 93. Let's move on to 94. All right, we are moving on to question 94. Oh no! Thanks to the lower price, 10,000 iTalks were made and sold initially, but after that, weekly sales actually decreased by 3%. Uh-oh. So this is the first time we've talked about a decreasing percent. So here's the thing. If something's decreasing by 3%, I'm following the same pattern here. Instead of taking a 1 and adding 3% expressed as a decimal, I'm going to take 1 and I'm going to subtract 0.03. That gives me 0.97. So here's the deal. My multiplier now is 0.97, and what that means is that there's no growth here. I'm only keeping 97% of what I had. So if you think about the bouncing ball, every single time the ball bounced, I think the one that we used recovered like 60% of its initial height. So that meant that it was decreasing in height by 40% each time, right? So I was concerned about what the height came back up to, so we're multiplying by it's keeping 60%. Same thing here. I'm losing 3%, but instead of dealing with that, I'm just going to say, look, if I'm losing 3%, I'm keeping 97%. So 0.97 is a 3% decrease every single time. So if I wanted to run this out for the weeks, right, I could change my explicit equation pretty simply, and I'm going to actually write the explicit equation right here. I'm going to say that T of n, the nth week, will equal the pre-sale, the 0th term of 10,000 units times 0.97 raised to the nth power. And this multiplying by 0.97 again and again and again, right, in the form of this exponentiation takes care of this for me automatically. So let's go ahead and do that on my calculator. I'm going to grab the number 10,000. And I'm going to multiply by 0.97 raised to the 4th power, and that will give me the 4th week sales. So when I raise it to the 4th power, I get 8,000. For week 4, I get 8,853 phones. And when I raise that to the 10th power, let's see, let's just go back up and change that to a 10. I like calculators. I get that that's 7,374 phones. So I can see that it's definitely the model that I've built here, right, is totally the explicit relationship is showing that it's decreasing over time. Next thing, write an explicit and a recursive equation that models the product's actual weekly sales. Well, hey, I just got part A done right here, right? This is completely the explicit rule, right? And says if you want to know the nth week, just take 10,000 and multiply it by 0.97 raised to the nth power. That's the explicit rule. If I want to write the recursive rule, it's a little different. Two pieces of information are needed. And I'm going to start with, well, I'll write the recursive part first. So in order to get to the next week, what we do is we take the week that we're at, so we take the t of n week, and we multiply that by 0.97. So in order to go forward, in order to get the next week, you simply take the week you're at and you multiply by 0.97. The other thing that you have to tell the recursive rule is that where you're starting, and instead of saying where I'm starting, I'm going to say right before I start, right? My pre-cells, I can say the t of 0 is 10, 1, 2, 3. So this works nicely, especially if you have a calculator, because you start with the 10,000 and you just keep multiplying by 0.97 again and again. Finally, it says confirm your explicit equation is correct by testing it using your results from part A. Okay, well, I actually did not get this value right here. I didn't get this value using the rule. I actually, on my calculator, I just kept multiplying again and again. No, that's not true. I actually used my recursive rule. So I'm just going to say, yeah, I did that. I did that. All right, last question. All right, so the last thing that I want you to include today is a response to 95. It says, in a geometric sequence, the sequence generator is the number that each term is multiplied by to generate the next term. This number is called the common ratio or the multiplier. And if you think about this with an arithmetic sequence, we had a common difference. So here we've got a common ratio or the multiplier. Whoa. Look back at your work from problems 93 and 94. What is the multiplier in each of these three situations? Next, what is the multiplier for the sequence 8, 8, 8, 8? Explain what happens to the terms of the sequence when the multiplier is less than 1 but greater than 0. That's an important thing. And what happens to the multiplier? What happens when the multiplier is greater than 1? And I want you to just write this down, write a response to that in complete sentences in your notes, and title it multipliers up at the top. So make sure you include this in your notes. So today, again, I'm looking for, we did them together, 92, 93, 94, and I want you to write a response for 95. That's it. Look forward to seeing you in class and online again. All I'm looking for you to do is just upload images of your notes today. Thank you very much. This is Mr. Roberts. Have a good day. I'll see you soon.